Hey guys, we're back. In this video, as I hinted to in the previous video you just watched, we are looking at applications of exponential growth and decay. So, beginning, let's look at a situation of bacteria growth. Now this is, I believe, something we see in probably biology. I can't imagine this being done in chemistry, but this is also something that's used a lot as an example when this is first introduced in Algebra 1 and Algebra 2. Just is looking at bacteria growth. So let's imagine we have a culture of 100 bacteria. Okay, and we place this bacteria in a petri dish. And the culture doubles every hour. All right, so this is our situation. So I'm not going to give you the actual question yet. So it's going to require us to think about what the model, what the function is of the situation. So let's see. So let's kind of break this up. After 1 hour, so we initially had 100. We double every hour. So after 1 hour, we would say we have 200. Okay, makes sense. After 2 hours, we're at 200, and we doubled. But I'm gonna write this in a different way. I'm gonna say that this is actually 100 multiplied by 2 multiplied by 2, which simplifying is 100 multiplied by 2 squared, and we know this ends up being 400. Okay, so we're gonna make note of this line here. It's after 3 hours. So after 3 hours, so the previous we were at 400, we're doubling, so we know it's going to be 800, but let's write this as 100 times 2 times 2 times 2, or 100 multiplied by 2 cubed. We know this to again be 800. And I'm thinking either you already knew or you have noticed a pattern here. We had 100 times 2, 100 times 2 squared, 100 times 2 cubed. So you can imagine, if I just generalize this for t hours, that we would have 100 multiplied by 2 raised to the power of t. And this is going to be our model, our equation for this situation. So we're seeing that we're doubling every hour, starting with an initial population of 100, and here is our equation. So we have our model. Now we can actually explore this situation more. Let's say that we want to predict the number of bacteria, or when will the number of bacteria reach 350,000? Okay, so mathematically, we're thinking of and this is essentially what we desire to know, is for what t value will make this equation work. We do know methods for solving this algebraically, we just might not remember them. But for now, looking at the graph that we see here in the screen, we find the solution to our situation. After 11.773 hours, again, we're looking at the intersection of the two graphs. After 11.773 hours, or this is essentially 11 hours and 45 minutes, the bacteria will reach a population of 350,000. And it's unrestricted. We know about exponential growth that is unrestricted. So we're saying that in this petri dish, that this bacteria is just going to continue to grow, even though we know probably that there is a restriction of some sort. Okay, so we use our graphing utility. Desmos was good here to show us where the intersection of the two lines, the two functions were, and that gave us our solution. So let's look at another scenario. This is possibly what I find more interesting than the bacteria growth, and that would be radioactive decay. Something I never really had much interest in it until I kind of looked into this example more. So with radioactive decay, the idea is, if you don't know what it is, it's the process that refers to an element changing from a radioactive state to a non-radioactive state, and again, a given fixed amount of time. And this time that it takes for half of a sample size to change its state, we designate this time frame an element's half-life, and that's what this next example is about. So I just studied real quick. There are two elements that have radioactive properties and therefore have a half-life, and that being radium and polonium. And there's a whole other list, and I'm not going to act like I know what the whole list is. I just know that this is definitely dealt with in chemistry, in physics, and other science fields. So let's look at this example. The half-life of a certain radioactive substance is 20 days, and there are 5 grams present initially. So we can see our initial value, and we can see the half-life. So we are confident, knowing and understanding half-life, we can say that after 20 days, we are at half of the initial amount. So writing this as, and you'll see why in a little bit, 1/2 of 20. So after 20 days, we are at 2.5 grams of substance. So let's say another 20 days have passed. So after 40 days, half of what we currently are dealing with, so half of 5, so half of 2.5, we can figure that out. So I'm going to rewrite this as 5 multiplied by 1/2 raised to the power of 2. You can see that. And I'm going to write this again as 5 multiplied by 1/2 raised to the power of 40 over 2, or 40 over 20. Okay, so I'm going to start looking for a pattern in our end result, and say after another 20 days has passed, after 60 days. So I want to write this half of half of half, okay, or 5 multiplied by 1/2 cubed, or 5 multiplied by 1/2 raised to the power of 60 over 20. And I'm thinking you're starting to notice a trend here. So this trend is, we just generalize it, after t days, we can say that we get a function or a formula for 5 multiplied by 1/2 raised to the power of t divided by 20. Okay? Now, this is a common thing for half-life, where we have 1/2 as our base, our initial value, and the actual half-life shows up as the denominator in our exponent, which is one interesting aspect of this scenario, is we have a fraction as our exponent. So question for you. How long will it take for there to be 1 gram of substance remaining? Okay. So we desire, after how many days will we have 1 gram present? So we know we're setting our function, 5 multiplied by 1/2 raised to the power of t divided by 20. We're setting this equal to 1. And we examine this, and really not being familiar with the algebraic methods, possibly, we can again use a graphing device to help us here. So as we examine the graph of this function, we find, again examining the graph, looking at the intersection between the two, we find that it is after 46 days, roughly, 46 days, that our 5 gram substance has been reduced to 1 gram. So there's a lot of applications. We have 2 scenarios here, one dealing with bacteria growth, the other dealing with radioactive decay and half-life. But when you enter class, we're going to be trying an experiment out. We're going to be spreading a rumor and seeing exactly, we've talked about how logistic functions can be used for rumors, but we're going to truly test it to see if, in fact, if we spread a rumor, do we get a logistic pattern, or logistic shape to our graph? Okay, so not much to talk about. Just knowing where these functions are coming from, knowing how we formed both of the functions. But if you have any questions or comments or concerns, post them into the Google Classroom, and I will see you then.